Professor DeLuca.
And I'm Professor Fusquetti.
Today on thechemistryassist.com we're going to do our first video on how to distinguish electron pair arrangements and their geometries and their assembly when we have lone pairs.
On Chemistry Assist, for facilitation of understanding of what each component represents, we have the white balls with the black stripes representing essential atoms.
For the bonds, it's going to be the same white ball just with a gold stripe across, and for the lone pairs, it's an X across the ball in a purple color. And for the bonds, this wooden stick represents the bonds between each component.
Now, each molecular geometry corresponds to a certain repulsion number. You either have a repulsion number of 2, 3, 4, or 5. Now, starting with the most simple one, I have my essential atom here. I will now show you how to assemble a molecular geometry in the form of a linear. So, we attach our bond, then we attach another bond on the other side, and we put two atoms on either side, and that way we form a molecular geometry that has an angle of 180 degrees. This is the most simplest form of a molecular geometry. We say that it has a repulsion number of 2 because there are two atoms on the other side.
Now we're going to continue on to the second electron arrangement configuration.
This one has a repulsion number of 3.
So we have our central atom and 3 bonds, which are 120 degrees apart, just like this. Okay, and now we're going to add our bonds on each end here, 3 molecules. So this arrangement with a repulsion number of 3 is called trigonal planar, and it resembles this form.
This will always have 120 degrees. Next up, we have the molecular geometry corresponding to a repulsion number of 4. Now, the name for this particular geometry is called the tetrahedral, and if you remember from your favorite subject of nomenclature, tetra corresponds to the number of 4, and therefore this bond has 4 other bonds. And this is going to be in a shape that looks much like a piano stool, and the bond angles are 109.5 degrees. This, I repeat, has a repulsion number of 4. The repulsion number always corresponds to the number of atoms that we have.
So the next one is our trigonal bipyramidal, which it has a repulsion number of 5. So once again, we'll start with the central atom. Similarly to the trigonal planar, we'll put 3 bonds at 120 degrees.
These are now known to be in the equatorial position.
And then we will put one on the top and one at the bottom. So if you can see through just the bond before we add the molecules on each bond, it's a similar shape to 2 pyramids if we were to connect each bond from corner to corner. So now we will just add the molecules.
The bonds in the vertical direction are known as axial. The bond angles between the equatorial bonds are 120 degrees, much like the trigonal planar. However, between an axial and an equatorial bond, it is 90 degrees. The final electron pair arrangement of this video will be that corresponding to a repulsion number of 6. Once again, we begin with our essential atom, and we begin to attach 4 bonds on each side, making a cross, much like the methane atom, which is CH4. However, we will now add 2 axial positions.
So once again, these 4 bonds are in the equatorial position. And as we could add, instead of having 2 triangle-based pyramids as we had previously in the trigonal bipyramidal configuration, now we will have 2 square-based pyramids where the equatorial position is now the base for both pyramids.
This is known as an octahedral. But wait!
In chemistry, not every molecule consists of perfect bonds like we saw in the electron pair arrangements previously. We have such things called lone pairs, which are electrons that remain unbonded that circulate the atom. When it comes to lone pairs, scientifically you cannot identify their exact positions. However, in our assembly of these molecules and chemistry, we give them assigned positions without identifying the angles, since we do not know exactly where they are.
Looking back at the previous video, all of the electron arrangements that we have correspond to a lone pair arrangement, except for the linear one. There will always be a minimum of 2 bonded atoms. So that being said, we will start with a lone pair on a trigonoplanar arrangement. We start with our central atom, as we did previously. Note that it has the exact same form as it did before. However, now we are placing 2 bonded atoms along with 1 lone pair. And its shape is considered to be bent, because whenever you have a lone pair, we imagine that it's not there. And the shape that we see with these 2 is bent.
Okay, so now we're going to move on to the tetrahedral arrangement. Since there are 2 types of geometries where we can have lone pairs, we'll just start with general shape.
It is important to note that just because there are lone pairs does not mean that the repulsion number changes. For the trigonoplanar, it was still a repulsion number of 3, and for the tetrahedral, still a repulsion number of 4.
So we have our piano stool like this, where we have 3 bonds at the bottom. This type of geometry is called trigonoplanar. Okay. Next, our second type of geometry with tetrahedral electron arrangement has another lone pair located at the bottom, and this geometry is called bent. As a fact, water possesses this type of geometry.
Now moving on to the molecular geometry of that with a repulsion number of 5. As we remember from the previous video, it has the form of a trigonal bipyramidal. So we start off with the equatorial positions, each 120 degrees apart. Now, it is important to note that the lone pair wants to find itself on the equatorial position because it wants to be further away from everyone else. The bond angles, as we remember, on the equatorial positions is 120 degrees, and between the axial, it's only 90 degrees. So, a lone pair will favor a further displacement of 120 degrees rather than 90 degrees. So, in the end, we have a form that looks rather like a seesaw. I say this because this is the way it would normally look. And if we were to ignore this, we have a regular old seesaw. Now, we also have a second case of lone pairs that, again, found on the equatorial position, will be on the other side. And here, we have something called T-shaped, right here. Because of the lone pairs, they will bend this more like that. There's also a third case of lone pairs, where we have a third one on the axial position, thus leaving us with only a linear shape of less than 120 degrees.
Okay, so now we're going to move on to our next electron arrangement, octahedral, which there are 2 cases where we could have lone pairs, so 2 types of geometry. Our first one is square pyramidal. So like the electron pair arrangement octahedral, we have our 4 bonds on the equatorial position, along with 1 bond we'll put at the bottom in this case. Our lone pair now is going to be the next bond on top. And this is called square pyramidal since it's a square-based pyramid at the bottom. And if we have the lone pair on top and we ignore it, it would still be a square pyramid. So we add our lone pair on top like this. These bond angles are supposed to be 90 degrees if we did not have this lone pair and this was a bond. However, it's going to be a bit less since they want to repulse this lone pair on top. So they're going to be bending towards the bottom. So we cannot identify exactly this angle, but we can say it's less than 90 degrees. Now the second case, it's called square planar, since we're going to replace this bond at the bottom with a lone pair. And if these lone pairs weren't there, it would just be like just a horizontal plane with 4 bonds. And these bonds, we can now say they're 90 degrees since there is the same repulsion on top and the bottom due to the lone pairs.
So this has been our video on the different molecular geometries and repulsion numbers that we have to show you. The photos are all found on our photo gallery on our website. We hope that this presentation has been of some help to you and that you may ace that quiz or exam.